Translation. Now, of course, a very important transformation in computer graphics is translation. It's moving objects, moving them in one axis or by some coordinates to one direction or to another direction. So by placing them in different locations in our scene or making them move around, so extremely important, right? And to illustrate it, the example here, for example, we have again this same geometry. We can move it to the right, we can move it to the left, or we could move it up and down. And you can see the matrix kind of does this interesting trick. So if we move it by 4 units up, then there's this 4 here. Or if I move it 2 or maybe 4 units left, then we have -4 here. But in computer graphics, it turns out that it's gonna be a bit tricky to encode in the linear transformation matrix. So before we get to this, imagine this scenario. Imagine we have just a 1D world located at y=1 line in 2D. So it looks like this. We have this one-dimensional world. These lines here, all they know is this 1D world. They have no idea that there is this 2D world around them. But we, as well, 3-dimensional beings, can of course see this 2D world. And they're all in this y=1 universe. And notice that all these points in 2D, they have the coordinates where the second value is 1. So 1, 1, 2, 1, 4, 1, 6, 1, and well, whatever point you have on this line, its second coordinate is 1. Now, something interesting happens when we do a share operation, share x on this space. So if we do share x by, well, we can define it by the tangent 45, but we could also say that it's by 1 unit. We put 1 up here because it's share x now. We move everything parallel to the x-axis. And if we do this calculation, we can see that it's x plus 1 times 1. So x plus 1. And the second coordinate stays 1. If we would have share in just any 2D space, we would share any 2D coordinates, then we would have some other value down here. It would be y, it would be maybe 7 or 10. And we wouldn't add just 1 to it, but we would add 1 times that coordinate. But because we're now only working on this 1D world, where all these points have the second coordinate as 1, then multiplying them with this matrix will always add this 1 to the x-coordinate. Or we could maybe use 2. So if we do share x by another angle, tangent of another angle, and that would be 2, we would put 2 here, then we would move everything by 2 units. So it would be x plus 2. And they would still stay on this y=1 line. They wouldn't like move out of their universe, or they wouldn't kind of like disappear from their universe into another line. They would all still stay on the y=1 universe line, but they would move by the amount we have specified in our share transformation, in our higher dimensional share transformation. And you couldn't really do it with any other like just linear transformation on any xy. They would have to have coordinates x and 1. And this is the trick that we use in computer graphics for translation, because our end goal is to have a matrix that if we multiply it with our coordinates would move our objects, our coordinates, by some amount we have encoded in the matrix. So we want to move them by some amount in x and some amount in y and maybe some amount in z. And we want to encode it in this matrix vector multiplication. So that's why this translation it's actually an affine transformation. It's not a linear transformation. It doesn't satisfy linearity just by itself. Like you can try it out. Like if you have a function that adds some value to one of the coordinates of the input, you can prove that this is not a linear transformation. So there wouldn't be any matrix that would just add values to the coordinates, because it's gonna be a linear combination. The result coordinates will be linear combinations of all the input coordinates. So that's why to do translation as a linear transformation, we want to move into this one-dimensional higher space where we add one more coordinate, which is always 1, and then we can add values from the matrix directly on top of the input coordinates. So in 1D we already saw this case. In 2D the translation column would be here. So what we want to add to the x coordinates and what we want to add to the y coordinates. And because the last value is 1, then this will just get added to the original x and y. And in 3D, very similarly, but now we have 3 coordinates. And you can then imagine that this 3D movement that we're doing is kind of this 4-dimensional share operation that kind of looks like movement in 3D, but well, in 4D all the space is just sharing kind of in this interesting way. And this might be very similar to now what we learned a couple of topics ago, these homogeneous coordinates, where if we have points, then we add one more coordinate to those points, and it's usually 1. And this is exactly what's happening here. So in order to do a translation, we move our original x, y, or regular coordinates into this homogeneous coordinate notation where there's 1 in the end. And for vectors it would be 0, and then you can see that if we translate vectors, their coordinates don't really change because they're just directions, they're not locations. Now all of this gives us a very good tool set to transform our geometry as we would wish. And this results in this affine transformation matrix, or this augmented transformation matrix, which you can see here. So we have this 4x4 matrix. This is why in the examples you also saw this 4x4 matrix. We have all our coordinates in this homogeneous form, x, y, z, and 1. So we can kind of investigate this matrix. So the linear transformation would be over here, and you can see that this part of the matrix does the linear combination with the input coordinates. So this is the linear transformation part. All our regular 3D scales, shares, rotations, we would encode here. Then we have this translation column. So this is this higher dimensional share which kind of moves our objects, which adds these values that are in this column to these coordinates. Then the bottom row usually is 0, 0, 0, 1, but we will change it a bit later in the material. So sometimes we do want to put some values down here as well. But it's for perspective projection. Like if you don't think about it right now, so right now you can just think that it has to be zeros, and then well, this last value has to be 1. Because if you would put anything else than 1 there, or 0, 0, 0, 1, then you would change this 1 down here. And then this result that you have, that would no longer be kind of this normalized point. It wouldn't be these first 3 coordinates, but it would be these first 3 coordinates divided by whatever value is down here. But as long as we keep it 1, when we divide this last value, they will stay the same. But regardless, this is this augmented transformation matrix. You should remember right now that there is these linear transformations here, this translation column, these zeros and 1, and we use it on the coordinates in this homogeneous notation. Now from this video you should understand translation. You can imagine translation as this higher dimensional share operation, and you know now where the homogeneous coordinates are important. So they're important for the translation to work as this linear transformation. We also saw the augmented transformation matrix that consists of the linear transformation part, the translation column part, well, the bottom row, and the order in which these different parts are applied. So the linear transformation is multiplied into the coordinates first, and then this translation column is added on top of that.